In this segment, we look at sources for timing vulnerabilities and timing attacks themselves. So we really just want to spend half an hour or so discussing possible strategies for timing attacks on RSA. We'll do that by first thinking about the general working principle of a timing attack on something that's much simpler, namely a pin system. And this is actually what ties in with this week's lab challenge. We move on fairly quickly from that. You can spend more time on that during your lab sessions, and then investigate what are causes for timing leaks, and then also how to exploit them in the specific example of RSA when we use it for decryption. So let's think about the general principle of a timing attack. A timing attack is a side channel attack, which means that we assume an adversary can observe certain characteristics of the implementation of some scheme that's related to some security functionality. The example that I've chosen here to start off with is that of an electronic lock of some sorts. This is a kind of principle that applies to many applications. For instance, if you get money out of a ATM machine, then you will have to produce two factors for authentication. One would be your bank card, and the other one typically is a PIN code that you have to provide. So in a sense, there is a sort of electronic lock included. In many other access control systems, you would also have to enter somewhere some PIN code or passcode to open a door or whatever. Online banking uses often still PIN codes, although luckily people have moved on from that. And so by and large, a lot of applications are secured by asking the user to supply some known code of some sort, and often this is just a very simple PIN code. So I think you're all familiar with this kind of system. So you typically have an N number PIN code. N could be 4, 5. It rarely is larger than any of sort of 4 or 5 numbers. How does that tend to work in practice? Well, again, you should be familiar. Typically, you're prompted to enter your code, and then afterwards you're either given access or access is refused. And after a number of trials, often your access will be revoked anyway. So let's think about, just as a sort of thought experiment, how would you potentially implement such a PIN checking system? Well, it would be quite natural to essentially write a routine that takes in the supplied number as a string of digits, and then check each digit against the known secret combination. And it would be actually quite tempting, and I think for many people quite natural, to sort of do this check digit by digit, and as soon as you encounter an incorrect digit, you could conceivably already abort the checking routine because you know it's wrong, the user input has been wrong, and abort and essentially just leave it at that. But is that really a secure solution? Consider now an attack where the adversary can measure side channel information, in the sense that the adversary can measure how long it takes the electronic lock to provide a response. If the implementation really works on the principle that you check each digit sequentially and immediately abort the routine as soon as you find an incorrect number, then it is conceivable that if your first digit is already incorrect, you would get a basically immediate response from the sort of electronic lock that tells you you're wrong. If you had, for instance, 2 numbers correctly, so the first and the second one, or you had the first correct and then the second one was wrong, then conceivably the response time would be slightly longer. And if you had 2 correct and the third one would be incorrect only, then again the response time would be longer. So if an adversary can measure accurately the response time of the electronic lock, or the program that essentially checks the PIN code, then it is possible that the adversary can make much more educated guesses about the PIN. Namely, the adversary sends a number to the lock and monitors the response time. If it gets an immediate fault or an immediate negative response back, it knows the first number of the PIN code must already have been wrong, so it can check another number until it hits upon a number where the response time is slightly longer, in which case the adversary has learned that the first number of the just supplied pin must have been correct, but then the next one was most likely incorrect. And in that way, the adversary has got a much better chance to reveal the pin code. And in fact, there's no longer a brute force search necessary. Each digit can in fact be tested individually, which brings the overall search space down considerably. Now, that may be a really simple example, but you wouldn't believe how many pieces of code you would still find out there where probably somebody thought that they were clever and implemented a pin or passcode checking routine in just that way. Check things digit by digit and return a negative response as soon as you encounter something that is wrong. So it's very tempting to make this kind of mistake. If we now sort of think a little bit about, well, how can we mitigate against such an attack, then the answer in this case comes, I think, pretty immediate. And the answer obviously is, well, make sure that you only respond after you have checked every single digit, irrespective of when you already know that a supplied pin is incorrect. It's another way of saying choose a response that takes the maximum amount of time that the routine can take. So essentially, produce a piece of code that runs in the worst case timing. In this particular case of a pin code, this is possible. We can definitely find out what is the longest time that the program can ever take to respond this was an incorrect code. And it's probably acceptable because the whole program won't take too long. But if you now think about that maybe a similar principle could be applied to many other types of implementations of some security functionality, you may begin to wonder whether it is actually possible for these other cases that you can actually find out what is the worst case response time, and would it be acceptable to always run your program in such a way that it is as slow as it can be? I think that brings us immediately to the first conclusion, and this is that defending against these kind of side channel attacks means that you have to write code that is less efficient. So let's move on and consider now timing attack according to such a principle against an implementation of RSA. The first question, I suppose, is what kind of reasons might there be in an RSA implementation that the response time or the execution time of decryption might not be constant? And we will sort of talk through this. Then we will sort of apply a sort of a simple timing attack to RSA and see how far we get. And it will turn out that we maybe have to be slightly more sophisticated, which will lead us to an attack principle that's called differential timing attack. And that is in effect a generic attack principle, so it can be used with any side channel. So that gives us then differential side channel attacks. This is the sort of attack that you are asked to do also in your coursework. So, but let's do things step by step, and let's look at why may there be timing variations in our RSA decryption code. So what sources for timing leaks might there be? I guess it's a matter of taste whether you start thinking about sort of high-level reasons or high-level functions that you have to implement in order to implement RSA, or if you sort of start from a more lower-level perspective where you look at might there be even reasons in the underlying hardware why there may be timing differences. And I have chosen here to take sort of the low-level view first. We know that although if we are writing software will of course be executed on some level on some hardware. So if you consider the various layers in which a program is sort of executed or represented, then you may write something in a high-level language such as C, but when you actually run it on an embedded device, such as the one that you're using in your lab, and for the coursework, then the C code will have to be translated into something that can actually execute on this device. In your case, this is sort of ARM code. And then the device itself is, of course, a piece of hardware. So the assembly instructions They have to be translated into some form of microcode, and that then runs onto some very, very real hardware. So there are somewhere some physical gates which represent zeros and ones and logical functions that operate on them. So on the lowest level, we have these kind of gates. Are they operating in constant time? Well, the answer is no, of course not. Some gates may, but many won't. Take as a simple example an AND gate. An AND gate will be 0 as soon as one of the inputs is 0. It doesn't have to wait for the other input as soon as one is 0. So the switching times for logical gates, they depend on the data. So we have got a very basic source for timing leaks, which is entirely down to the type of logic technology that we use to implement devices. There might be reasons which are maybe then slightly higher, on a slightly higher level than the gate level. For instance, if you think about the difference between multiply and square, even if you have a hardware multiplier, it turns out that squaring operations take a slightly different amount of times. They are slightly faster than squaring operations, even in dedicated hardware. Next step up. What about loops? We've got a for loop normally when we are executing RSA, whether it's decryption or encryption, doesn't matter, because we have to run through the bits of the secret key. Obviously, if there's a longer key, so with many more bits to be processed, execution time will be longer than for a shorter key, clearly. And we do have a conditional branch in our key-dependent exponentiation. You will remember, if and only if a certain key bit is said to be 1, then we are executing a multiplication in this specific round of a for loop. And then finally, we have got this oddity in our Montgomery multiplication, where by and large this is sort of constant time, except for the odd circumstance, or the odd sort of occurrence, where an intermediate value happens to be just a bit larger than the modulus n, in which case an extra reduction has to be performed. So here on the slide, you can see a number of bullet points, which all sort of tell you that it is nearly inevitable that your RSA implementation will not be constant time unless you make a real effort to get rid of all sorts of little sources for timing variations. How can we use that? Well, so you can see here on my slide, I have just pasted in the left to right binary algorithm as a reminder. And what if we can simply observe the execution time of this algorithm running? Well, as I said, we've got a number of sources for timing variation in this algorithm, and maybe the most obvious one to think about and to exploit ad hoc would be to say, well, clearly, because if and only if a key bit is 1, we do the multiplication, we should be able to derive the number of multiplications from an overall execution time. It kind of makes sense because typically we know the length of the secret key, which means we also know the number of squarings that we will do, because we do that for every bit. And then everything else must be due to multiplications. So certainly, if we are able to play a little bit around with a device, if we can assess how long does a squaring maybe take by having another device that we have under control and where we can do some timing measurements from, then by observing a fresh execution time measurement from an unknown key, we should be able to work out how many 1 bits are in the exponent, which means that we can reveal the exponent of the secret RSA key. This already sounds quite good, and in fact it is already quite a substantial information leak, but RSA keys are very long, and knowing the Hamming weight of an RSA key means you still have many possible RSA keys afterwards. So it's not good enough for a real practical attack. It's certainly a theoretical one, but it's not good enough for practice. So the question is, can we do better than this? And the answer is yes, we can, by utilizing this principle of a differential side channel attack. And this is a really important picture here. It really visualizes the thinking that we use for any differential side channel attack. So whether it's differential timing, differential power, differential EM, it really doesn't matter. Any sort of differential attack uses this kind of principle. And if we really wanted to sort of push it, we could also say that many other side channel attacks somehow follow this way of thinking. So I want to talk through this somewhat slowly. The picture consists of several components. On the left-hand side, here, we have got the device under attack. This is just a word for whatever the target really is. In your case, it's an M0 processor that's mounted on our scale board. It could also be a mobile phone, it could be a car key, it could be your bank card, it could be your laptop, it really doesn't matter. It's somewhere a device. The sort of attack that we are really focusing on is an attack that reveals the secret key. Now, this is just one possible way of breaking cryptography, of course. It's the strongest way. As soon as you have revealed the secret key, you can do all other things as well and thereby violate all sorts of security notions. But there are other side channel attacks which do not attempt to reveal a secret key. They actually want to reveal the input data of something, which would be more corresponding to breaking the notion of in CCA or in CPA. But here we are going for something stronger. We are actually going to go for key recovery, full key recovery. So we've got our device and we've got the key in there, and which is written in red because that's sort of what we are after. We don't know that. The picture also shows you that there is data going into this device. And side channel attacks come in all sorts of different ways and variations. Sometimes we can just observe data going in, but we have no control over it. Sometimes we can choose the incoming data specifically. Sometimes we actually don't know what the incoming data is at all, but we may be able to see something of the outgoing data. So there are all sorts of variations possible. For us now, for the attack that we will concretely look at for RSA, we assume that we actually can even choose the attack, can choose the input, although we'll take not any great advantage of that. And then you can see the outgoing arrow here is indicating to give us the real execution time. So we are able to somehow time this fairly precisely. And the execution time is from the point in time where the data has been received to the device executing RSA decryption and then giving us the output. So there's a little bit of variation potentially on it, but otherwise we are doing fairly precise measurements. Again, as I said, these attacks come in all sorts of variations, and people have demonstrated differential timing attacks over a network, where of course your real execution time that you measure wouldn't be measured on the device, but somewhere else on the network, and you would have huge timing variations because the network traffic is also not constant time. And then here on the right-hand side, we have some form of model of the device under attack. And I have drawn that as though it was a sort of a thought process, a thought model, a thought experiment of an adversary. And this indicates, again, one variation of how these attacks might be executed. Maybe the adversary has only got a very high-level idea of how the actual device works. So the timing predictions, the hypothetical execution time that this model will output, it may be very coarse. It mightn't be very precise. It could, of course, also be that this model of the device isn't just some idea or some thought experiment of the adversary. It could well be that the adversary will simply go and buy an identical model of that device under attack that they can fully program. Yeah, in which case, the hypothetical execution times might be much more accurate and much more comparable to the real execution times. But the way in which we use this model is that we supply it with the same input data as the real device. And the only thing we don't know about the real device is, of course, the crypto key, the secret key. So what can we do there? Now, there is something that's called a divide and conquer attack. And the idea here is that rather than having to guess the secret key, this long thing, the 1000-bit secret key D of RSA in one go, which is impossible, which would just take too long to have to the n guesses if n is over 1000 bits. We can make predictions about the device's behavior by just actually guessing a few bits, maybe just one at a time, in fact. And Maybe it's sort of obvious to you, maybe not, but this is possible because if you think of how, for instance, RSA exponentiation is typically implemented, if we use the left to right binary algorithm, then to say something about the timing behavior of the square and multiply steps in the very first iteration of the for loop, we don't have to know all of the key bits. In fact, we just have to predict a single bit, and then we can think about, well, maybe this multiply will take place or not, or maybe there will be an extra reduction somewhere in a Montgomery multiplication or not. And similarly, for other crypto systems, it's typically the case that the operations that are used to implement the system do not require the full use of the crypto key in any single step. This is because the keys are simply too long, and we don't have any instructions available that deal with thousands and more bits at any one time. So when crypto gets implemented, the keys normally get chunked up in some shape or form, and implementations only use a small chunk of the secret key at any one time. And this really enables a side channel adversary to do key recovery attacks. So we have got our model somehow, and we will describe such a model for RSA in a little bit. We get the hypothetical execution time, the predictions from it, and we are going to somehow compare it to our real execution times. And the thinking is now quite simply as follows. If our key hypothesis here for our model corresponds with the hypothesized key bits in the real device, then our predictions here should really correspond to what the real device is doing, which means that these two data sets that we have here should resemble each other somehow. Whereas if the key bit guess here was incorrect, then our predictions here make no whatsoever sense, and hence the hypothetical execution times that we are producing, they shouldn't correspond at all to the real execution times. We hence need to somehow analyze these two data sets, and we do that by using a so-called distinguisher, which is often a very, very simple statistical process, like, for instance, using correlation. If these two data sets show high correlation, then there must be some correspondence between them, and because the only thing that we are guessing, that we are unsure about, is the key bit, this indicates that our key bit guess was correct. Whereas if a correlation analysis shows that these two things have nothing to do with each other, then most likely our key guess was incorrect. So this really is the thinking. There's nothing more behind a differential side channel attack. It's really quite simple. But we need to somehow now try and put this idea, this process into practice. So we need to choose a set of ciphertexts. We need to produce a model which relies on guessing only a few bits of the key, and we call this key hypothesis. With this key hypothesis and some known inputs, we calculate just a few steps or iterations in the case of RSA of the square and multiply algorithm. And then we use some feature of the intermediate values to sort of make predictions about, is this going to take longer or shorter? And this will give us some hypothetical execution times. The device will decrypt the same input, so the same set of ciphertexts, and then we do our analysis, which essentially is a comparison between the real and the hypothesized timings. And based on our analysis results, we will decide whether our key bit guess was correct or incorrect. So, there's a really nice paper out there, which in previous years students had to find, read, and then implement as their first challenge, or one of their first challenges. And it's a paper by Dehm et al. And they essentially took the idea of a differential timing attack, which was originally proposed by Kocher, and described it in a very accessible way. And they describe it step by step. So they are very explicit about the device under attack and what it does, which I have here on the left-hand side. So the device under attack does the left-to-right binary algorithm. And then a model, which is here on my right-hand side, is also doing the left-to-right binary algorithm, but because we only have a little bit of the secret key known, we cannot do all the steps. Remember that in the left-to-right algorithm, we always assume that the MSB of the secret key is 1. So we know the first key bit already. So we know I minus 1 bits of the secret key, and we are guessing the ith bit. Which means that we have got two options. It can either be 0 or 1. And here on my slide, I've written it down in a slightly more generic way already. So I'm not assuming we just know the first one and then we are attacking the second. Here I just write it down in a more general way. We know I minus 1 bits of the key, and now we are guessing the ith one. So you can see our two potential keys. They are identical in I minus 1 bits, and they differ in the ith bit. One is 0, one is 1. And then our model is going to essentially use both keys to produce two different data sets. And so you can see here in the algorithm, you can only do sort of a certain number of key bits, namely I key bits. Okay, so what are we actually going to exploit? It would be tempting to just rely on, how many multiplications are there? But we already discussed this. We can't just rely on the fact that multiplications only occur if key bits are 1, because this will only ever give us the Hamming weight. But there's another feature which we are aware of, and this is the fact that in Montgomery multiplication, occasionally we have to do an extra reduction. So we are going to configure our model to see whether in the ith step there is an extra reduction or not. And we know that if there's an extra reduction, then this if statement has to be executed. So the timing of the overall routine must be longer than if this is not happening. So this will be our differentiator. We don't need anything else. Now there are two options of when this could happen in the ith step. It's either in the square or it's in the multiply. A lot of people would say, well, let's just go for the multiplication. Yeah, that's easy. Because if and only if the key bit is 1, then the multiplication will be executed, which means if we check timings there, then we can directly conclude on the secret key bit. So here on the slide, you have again, the left-hand side is the view of the device under attack, which in the ith step will execute here the Montgomery multiplication, and it may or may not have a reduction. And here our model has to run sort of twice, once for each key bit guess, and then for each key bit guess, it will sort of check if in this line it will do an extra reduction or not. This is not quite true, because if our key bit guess is 0, it will never go in there. So maybe choosing the multiplication isn't such a great idea, because it means that we can't get any distinguisher values for key bit guess 0. But never mind, let's persevere with the idea anyway and see what we get. So, okay, we have our device under attack, which, if the key bit is 1, will do Montgomery multiplication here in this step. It will go into the step and do Montgomery multiplication, I should say, and then we check whether an extra reduction is carried out or not. We do this by executing the model and making the assumption that the key bit is 1. Yeah? And so all what we do is we output, our model just outputs whether there's a Montgomery reduction or not. It doesn't actually tell you how long something will take. You can literally give a binary output for 0 or 1, depending on whether the reduction takes place or not. If we are correct with our key bit guess, if that ith key bit really was 1, then our predictions here are of course correct. Yeah? If our prediction here was incorrect, so the ith key bit was 0, then the device under attack never actually went into this particular branch. And so all of our predictions here are meaningless. So the idea of a differential attack is still sort of correct. This still works out. Okay, so how are we going to measure now whether or not our two data sets are the same? I would say intuitively, you would probably just go straight away for correlation. However, in that paper, and in many parts of the literature, people use a distinguisher that is based on the difference of means test. And because it's such a well-known technique, I want to introduce it here, although I think it's not the necessarily most intuitive way of doing things. So bear with me. Okay, so our distinguisher looks at differences between averages in datasets. And it produces a so-called distinguishing vector, which in the case of RSA will only have 2 elements because there are only 2 key guesses. So the distinguisher takes in the real timing measurements, which I call T, which are based on the correct key, which I call K star, and then some input X. And it will also take in the data set, which comes from the model, which is based on a key guess K and the same inputs X. And it will do that for both key hypotheses, so hence it's a 2-element distinguishing vector. An attack successfully identifies a key bit Ki star if you can reliably say the distinguishing score that corresponds to the correct key bit guess is larger than the distinguishing score of the other key bit guess. So this is our success criterion. Whichever distinguishing score is larger will indicate to us the correct key. And again, this is sort of notation that's frequently used, and that can be applied to a number of distinguishers, even if they're not based on averages. Okay, so let's look at an example with numbers. I've got here sort of written out how our distinguisher will really work. Our distinguisher will take in the set of measurements that we have from the real device and the set of predictions for each key hypothesis. And we configure our distinguisher to do the following. We'll take the set of measurements and we partition it into two classes. One class are the measurements for which our prediction tells us that there should be a reduction, and the other class of measurements is the one where there should be no reduction. We average over these two classes, and then we take the difference and we take an absolute value. That's how our distinguisher will work. Very, very simple. And I said there are some concrete numbers, and you can see here this is sort of the example in the table. I completely made these numbers up. They've got no real meaning. So I just randomly took some numbers here, and these are the timing measurements that we observe. And then I also specified a behavior of the device under attack. So the red column here is something the adversary wouldn't know. Yeah, but I've put it in here anyway, just to illustrate the working principle. So the assumption is that on the first measurement, in the ith bit that we are attacking, a reduction took place in the Montgomery multiplication. Here also a reduction took place, in the next one no reduction took place, and so on. Now the blue view is really what the adversary sees and does. So the adversary has got two choices for the ith key bit, it's either 0 or 1. I've already pointed out that if the ith key bit is 0, there's nothing we can predict about the properties of the Montgomery multiplication in the multiplication step, because it just doesn't take place if the ith key bit is 0, right? You don't go into that branch. So only if the key bit is 1, you can make a sensible prediction. And so if the key bit is 1 and the I-1 previous key bits were revealed correctly, then we will make absolutely correct predictions here. So the predictions that the adversary makes here, they totally mirror the behavior of the real device. And then the adversary computes this distinguishing statistic here. And typically you would just get all your measurements in and then average over the entire set, basically. But you could also do it sort of little by little. So whenever you get a new measurement, you can sort of update your distinguisher, your distinguishing value here. That's also possible. And this is what I'm showing here. Yeah, it's the sort of the online computation of the distinguishing score. Let's go through this step by step. So the first measurement that we receive is 12. It's in the category where you have a reduction. So in the reduction set, there is the measurement with value 12. In the no reduction step, there's nothing. So the average of 12 is 12, minus 0 is still 12. This is our distinguishing score here at the moment. We get our second measurement in, that's 14. So we now have got two measurements in the category with reduction. We've got nothing in the category with no reduction, so this is still 0. But here we have got an average over 12 and 13. About 12 and 14, which gives you 13, because 12 and 14 is 26, and half of it is 13, so that's the average of 12 and 14. So the distinguishing value here must be 13. Now we've got our third measurement. This is now 8, and this is in a different category. So this is now in the category with no reduction. So we have got the average of the first two measurements here, that's still 13. The average of 5 is 5. So the average of 8 is 8, and so the result is then 5 here. And so we can keep going. We get another measurement in with 12, which goes in a pot of measurements with reduction. So it slightly changes the average here, and then -5 gives you the new number, which is 4.67, and you can calculate the last 2 steps yourself. So at the end of this process, we have received 6 measurements, and our distinguishing score for the key guess 1 is 4.25. And now we are supposed to make a decision. Is that a large value or is it a small value? If we consider it to be large, then it means this is probably the correct key. And if it's considered to be small, then it's not. So we can only make this decision really bearing in mind distinguishing scores that we would have revealed from the previous I-1 bits. Otherwise, we've got no comparison here. So there's another example with the same setup. We are still attacking the multiplication, but this time in the ith round, actually the key bit had been 0. So there is not really a reduction taking place in a multiplication, but here these reductions would maybe relate to the squaring step. Now here the adversary, obviously by guessing 1, makes a mistake. The predictions here have got nothing to do with the device behavior. And now if we look at our distinguishing score with sort of this setting, then we can see the distinguishing score actually is only 2.33. So you can see the distinguishing score when the key guess is incorrect is lower than when the model prediction was correct, and the distinguishing score will be higher. So it sort of works, but it's not ideal because if we are attacking the multiplication step, then this leaves us in a problem when actually the key bit prediction is 0. So can we do better than that? And the answer is yes, of course. What we need to do is to move on and look at squarings. So this slide here just summarizes our results for multiplication. And we want to move on and now look at could we ever attack actually the squaring step? So suppose again we have already correctly revealed I-1 bits and we want to attack the ith bit. We want to do that by attacking the squaring. How would we actually do that? Well, we can't really. So this here shows you the for loop up to the ith round. We can't really attack the squaring directly in the ith round because it will always take place irrespective of whether the ith bit is 0 or 1. So this here, attacking it here really doesn't work. But if the ith bit is 0, then in the ith round, this if wouldn't be executed, and then in the ith plus 1 round, the squaring would essentially rely on the previous values. Whereas if the ith bit is 1, we would be going into this if. We would be hence multiplying in the ciphertext, and hence in the ith plus 1 round, this m here would be different. It would no longer be the m here, it would be a new value of n. So we can attack the squaring, but if we want to attack the ith key bit, we need to use the squaring from the ith plus 1 round. So let's do that and see what happens. Again, I've got sort of a simple example with randomly made up timings. I've again specified the device behavior for the ith key bit. And this is what the adversary wouldn't know. So the red thing is hidden from the adversary. And the blue view here is what the adversary really calculates. So there are 2 guesses, again for the ith key bit. Either it's 0 or it is 1. And depending on the prediction, the model of the adversary would spit out something. And I made this up, obviously, as well. This is just an artificial example. And you can see that, assuming that the ith key bit in the device was also 1, the one guess is completely correspondent to the actual behavior of the device, and the 0 guess does not quite correspond. It corresponds quite often, yeah, that can happen, but not always. So then I've got the 2 distinguishing scores as the adversary would calculate it if they do that iteratively, so adding 1 measurement at a time. And we can see that after 6 measurements, the distinguishing value for the 0 key guess is just over 1, whereas the distinguishing score for the 1 key guess is actually 4.25. So here with our rule, the larger distinguishing value indicates the correct key guess. This works perfectly. And here I've got another example. This I don't want to run through. I think it would probably help you if you would sort of pause with this slide and then sort of work it out, maybe with the calculator yourself, so you are completely familiar with how to use this distinguisher, which is based on just differences between averages. It's really, really simple, but I think without actually doing once per hand, you may struggle with it if you maybe come to use it in your own attack that you will have to implement. So it really makes sense to sort of run through this slowly. Finally, I did mention on beforehand that I chose to show you this particular attack with the sort of distance of means test as a distinguisher because it's so incredibly popular in the literature. And we will discuss later why this is. But there is a much more intuitive alternative, I think, and I would encourage you also to look at this. And I think for your concrete attack, then on the RSA power traces, correlation is a much, much wiser choice. So rather than relying on this distance of means test, you could also essentially directly correlate model predictions to real traces. I will now just briefly go back. Our model predictions here, I've written them always down as sort of in words or as strings, so it's yes or no. But of course, these are just two categories. We could also simply encode them by values 0 or 1. Or if we know how long a Montgomery reduction actually takes, we could take 0 and the actual value of this extra reduction step, which might make things better. So with this in mind, we could then plug in, essentially in our distinguisher, just the Pearson correlation coefficient between our measured traces and the model predictions. And I have written out for you the definition of the Pearson correlation. It's just a covariance standardized by the measurement and the model prediction variances. It's nothing complicated. I hope you will have seen it somewhere else before. And we plug in our model predictions now as they are values 0 or 1 or 0 or something else if we can do better than that. So here's again an example which is, made up artificially. You will be familiar with the numbers by now. I've now encoded the model predictions as 1s and 0s rather than reduction and no reduction. So you can see 1 is yes, and in a correct guess, you will sort of see a complete correspondence between the predictions and the actual behavior. And then we can calculate the correlation, a Pearson correlation between this vector here and this vector, and this gives you the value 0.21. And if we calculate the Pearson correlation between this vector here and then the measurements, then you will receive as a result 0.85. And you can see that the correct key guess is indicated by a higher correlation. And then here, for instance, we use something where the model says 1 for a reduction, and 1 for no reduction, and 3 for a reduction. And then you can see that, of course, the results here change. Yeah. And depending on, what is correct and incorrect, this will sort of emphasize or not your correlation profile of the correct key guess. If you are making incorrect assumptions about the model behavior, then this may not actually help your attack. And this is one of the sort of key learnings that people have taken over the years from side channel research, that maybe the statistical method that we use to differentiate correct and incorrect key guesses based on comparing real traces and model traces, the statistics maybe don't matter so much, but how accurately we model the true device behavior, this makes a huge, huge impact on the success of attacks. So the quality of the model is absolutely crucial for the distinction between correct and incorrect key guesses. There are all sorts of simple models available. So we used reduction, no reduction, which is the same as 0 and 1. And we can sort of improve on that, refine on that by maybe playing around with the device under attack. And this sort of process is called profiling, and we may use this later on at some point. So a summary. We looked at different timing attacks on RSA and also on the pin code example, and sort of the most interesting attack that we looked at was really the differential timing attack. This is the blueprint for all sorts of differential side channel attacks, and what you are doing with AES in the lab will follow exactly this principle. You will also have to choose between a difference of means test for a distinguisher and a correlation analysis as a distinguisher. You will have to think about how to best model the device that you're attacking. And then you will have to sort of make decisions about, well, how many measurements am I going to take? We haven't really talked about this today, but these sort of little steps, you will have to sort of consider all of them in your own coursework. There are timing challenges. There's a timing challenge course lab sheet available for you. It's not related to RSA. It's related to the pin code example, but you can, definitely go ahead with this one.